Okay, guys, this is a big day, man. This is not easy. It's a tough concept, so I need you to focus up. I need you to pay attention, some solid attention here today. The first part, not so bad, but once I get rolling here, you can't just kind of half pay attention and just fill in your notes and not really think about what you're writing, okay? Um, I'm starting on page 349. Is blood type like a card game? Now, these are questions on page 349 that just basically say, determine whether or not the given scenario is a binomial setting. Okay, part A. Genetics says that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a 25% probability of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. Okay, is this a binomial setting? Is it binomial? Is it a success or failure? Yes, because it's type O or it's not O, right? It's O or it's not type O. Independent, they said it's independent. The word's actually in the sentence. Is there a set number of trials? Yes, and I'm going to write n equals 5. They're having 5 little brats. And is the probability of success the same every time? My answer is yes. The probability of success is equal to 0.25. So yes, this is indeed a binomial setting. Let's go to part B. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time and record the number of aces that you observe. Well, if we're turning over the first 10 cards, we're not putting them back in. So every time I take a card, when I go to take the next card, there's less cards available. That's not independent. So I'm going to tell you right now, that's a fat no. It is binomial. Their aces are no. It is a set number of trials. I'm taking 10 cards. But it is not independent because the probability is not the same every time. All right. Then we got another example here. From A. Oh, we're just jumping off from A, so I'm going to put the book down here. Here we go. From A. A success is having one of their kids having type O blood. Probability of success is 0.25. There's a set number of independent trials, and that is 5. They're having 5 little brats. Okay, let's find the probability that 3 of the 5 kids have type O blood. Write the notation for that probability. It goes like this. Probability that x equals 3. That's what I'm looking for. The probability that x equals 3. Look right there. This is a very difficult probability question. Yesterday in class, we chose to use a simulation, but that was for greater than 3, not just equal to 3. We're going to need 2 of these 4 probability formulas from last chapter. Okay, so I'm going to write in these formulas. Probability of A and B was sometimes equal to the probability of A times the probability of B. That was when trials were independent. If they weren't, you had to go the probability of A and B was equal to the probability of A times the probability of B, given that A happened if they're not independent. Okay? The second set of formulas was probability of A or B is equal to the probability of A plus the probability of B. You were allowed to add, but only if they were considered mutually exclusive. All right? Or if they weren't, you had to go the probability of A or B had to be the probability of A plus the probability of B, but then you had to go minus the probability of A and B, because what happens is you count the intersection here and then you count everybody in the intersection there as well, so they've been counted twice. So you have to subtract them off once. Okay, I'm going to tell you that if one of the bins scenario things is that they're independent, we're not going to need that formula. That should make sense to you guys. And we're going to find things that are mutually exclusive. So we're actually going to use these 2 formulas in a very big way on the next page. Ready? Here we go, people. This page is a monster. I mean, it is a monster. So I want you guys to have your best focus here. You ready? Let me turn my page so I can write this in. Here we go. The probability that x is equal to 3. Well, that would mean the probability that we have O as a blood type for one little brat, and O as a blood type for another little brat, and O as a blood type for a third little brat. And then we got 2 more little brats. So we got to have any other blood type, so I'm going to call it not O, and any other blood type, so I'm going to call it not O. That's the probability that I'm kind of looking for. And they tell me that all these kids are independent. So I'm allowed to multiply the probability of O times the probability of O times the probability of O for the 3 little brats with blood type O times the probability of not having O times the probability of not having O. I am allowed to multiply them all together because I was told they're independent. That will always be true in a binomial setting because we said they have to be independent. In fact, that's the reason why we want them to be independent, so that we can just multiply them together. With and probabilities from the last page, you multiply. That's the truth. So isn't this 0.25 times 0.25 times 0.25? We were told the probability of a kid having type O is 0.25. And then 0.75 times 0.75 for the 2 kids not having type O blood. I put that in my calculator, get 0.0088. Okay, but that's not the answer. It's too small. That answer that we just got, everything we just did is legit and we're going to use it, but it's too small. What we just found is the probability of having type O and type O and type O and not O and not O, but we found the probability that all five kids are born in that order. What if they're not born in that order? That's another option, isn't it? So I'm going to take a pause and I'm going to stop the video and we'll do it all in the next video.